Okay, the peculiarity of this problem here is that we're given a function. Actually, it's a very simple function. It's just a rational function in which the denominator never vanishes, so it's a well-behaving function. But that's not the function we want to plot. We want to plot these two other functions, which are defined in terms of this f. In this one here, what we do is we fix a value of x, and then we find the supremum of the values of the function on the right of x, and that is the value of the function g. And the function at h is the same, but we take the infimum, right, of these values, right? Okay, so we'll first make the plot of this one, and then we'll decide how to plot this one, or what did they look like. The question about the domain and the continuity and the differentiability of this function is solved because it's a rational function, and as I said, there is no zeros on the denominator in the real line. So the next thing we need to do is to calculate the derivative to decide on the behavior of this function, right? Well, perhaps first of all, let's try to see if there's a horizontal asymptote. Okay, so we take the limit when x goes to either plus or minus infinity. For both happens, the same thing happens. The degree of the denominator is larger than the degree of the numerator, so this limit is always 0. So y equal to 0 is a horizontal asymptote. Okay, no vertical asymptotes, of course. And then the next thing to do is, as I said, is calculating the derivative. This is a quotient, so that's 3x squared minus 1 plus x times 2x, okay, divided by 3 plus x squared, and that is 3 plus x squared minus 2x squared, divided by 3 plus x squared. So the numerator is 3 minus 2x minus x squared, right? So x squared here minus 2x squared there. So we have this, and this is divided by 3 plus x squared. Actually, because of these two factors, we could just write this as 4 minus 1 plus x squared, right? Over 3 plus x squared, because the square of this is the square of x, right, with the negative sign here. Then twice x times 1, so this is 1, again with the negative sign, and then minus 1. Minus 1 plus 4 is 3. So we can write this like this, which allows us to factorize this in a very simple way, because this is 2 squared. So what we have here is the difference of 2 squares, which is the sum times the difference. The sum is 3 plus x. The difference is 1 minus x. Okay? 3 plus x squared. Right. We can check this. If we multiply this, is minus 3 plus 1 is minus 2. That's correct. Then minus x squared, and then 3. All right. Now, the denominator is always positive. We don't worry about that. The numerator is positive or negative depending on where the x is. So according to this, what we have is 2 points, negative 3 and 1. On the left of negative 3, both these terms are positive, right? No, sorry. This term is negative. Okay, on the left of negative 3, this term is negative. This one is positive. So the function is negative there. So here the function decreases. The derivative is negative, the function decreases. Then between minus 3 and 1, both these factors are positive. So the product is positive, the function increases. And finally, when x is larger than 1, then this factor is negative, this is positive. So the product is negative and the function decreases again. So x is equal to minus 3 is a local minimum, and x equal to 1 is a local maximum. Okay, right. If we calculate the values of f at those points as minus 3 and at 1 and and minus 3, the value is 1 minus 3 is minus 2. Then down here we have 9. 9 plus 3 is 12. Minus 2 over 12 is minus 1/6. And f of 1 is equal to, we have 1 plus 1 is 2. Okay, and down here we have 4, so 1/2. This is 1/2. Right. We have basically all the relevant information to plot the function. The function looks like this. Okay, so this is what the function looks like, right? The two critical points are this minus 3, okay, and the value of this is equal to 1/6, minus 1/6, okay? And the other one is 1, right? This point here is 1, and the value it takes there is 1/2, okay? 1/2. So this is the picture of the function. Function decreases up to here, increases, then it decreases, and y equal to 0 is a horizontal asymptote. So this is the behavior. But now we want the two plots of the g and the h, right? So what we have to decide what these functions are. And remember, what we have to do is we fix an x and see what happens on the function on the right of this x, and find the supremum of this function, okay? So let's say that we are here, okay, at a point here, right? If we look at the supremum of the function on the right of this, well, the supremum of the function is this value. And it is so up to x equal to 1, and including x equal to 1, right? So g of x is equal to 1/2 when x is smaller than or equal to 1. Any x that you take here, the supremum is this value, right? However, if we cross this point, let's say we are here, right? The supremum is precisely the value in the function it takes at that point, because the function is decreasing. So the function coincides with f of x. H is the same story, but it's the infimum, right? So we sit here, and what is the infimum of the function when we look at the right? Well, the infimum is this value here. That's the infimum value it takes. So it takes the value minus 1/6 for any x smaller than or equal to -3. Now, between -3 and this point here, let's see what is this point. This point is where the function is 0, and since the function f is 1 plus x and then has 1 plus x in the numerator, x is equal to -1 at this point. So this point is -1, right? So up to this point, the infimum of the function is just f of x, okay? It's the value of the function itself, right? But once we cross this, the infimum is 0, because the function decreases on the infinity towards 0, right? So once we cross this point, let's say we sit, for instance, here, or even here, right? The infimum of the function is the value it takes at infinity, which is 0. So the function becomes 0 when x is larger than -1. So these are the two functions, and we can plot them, and this is what they look like. Okay, this is what they look like. As I said, let me put it here. As I said, well, let's go to the g, right? G is up there. It is constant equal to 1/2 up to this point 1, which is where the maximum is, and then from then on, the function coincides with the original function f. If you go to the function h, which is the infimum, well, takes the value of constant equal to minus 1/6 up to the point where you reach the minimum, which is -3. Okay, then it coincides with the value of the function. Okay, and then from this point on, it takes the constant value equal to 0 because the infimum of the function on the right of this point is equal to 0, of any point on the right of this. So this is the function g, this is the function h. Both functions, by the way, are continuous, right? By the way they are defined, they have to be continuous, but they are piecewise continuous. I mean, they have the different definitions in different regions.